hello, good evening everyone. Welcome to the most comprehensive preparation app for all exams, BYJU'S Exam Prep. And warm welcome to the PYQ series for computer science aspirants. Join the session quickly and mark your presence. I am waiting for you all to join the session. Soon after you join, we will start the session. Meanwhile, in this session, we will be solving one of the interesting subject. Generally, students feel this subject as difficult, that is computer organization and architecture. From this subject, we will be solving the last 5 years, 2022, 2021, 2020, 19 and 18 PYQs. Guys, the most awaiting Maha marathon is getting started. The complete details about this Maha marathon, how you can utilize this, and when the classes happens, how many classes per day, how many questions we will be discussing, when what subject will happen, every detail about it will be disclosed to you guys tonight at 10 p.m. We all are coming live at 10 p.m. to present this Maha marathon for you. So stay tuned at 10 p.m. Catch us live to get complete detail. Our expert Mr. Joshit Singh will be sharing you how to ace GATE 2024 in first attempt, the tricks and tips for this. Okay, there is a mega workshop by Mr. Joshit Sir tonight at 8 p.m. So 2024 aspirants, you may join and get the tips from the experts. Our test series, which is a pack of almost 4,000 plus questions, that includes 40 plus full length mock tests and 30 plus subject wise tests with virtual calculator with detailed analysis. Every question is at GATE level. So avail our test series by visiting our BEP app or website. Okay. So I am Satya with 15 plus years of teaching experience, mentored more than 35,000 students all over India in the GATE and PSU segments. I am qualified in GATE, UGC NET, SET and certified by Cisco. This is quick brief about me. So guys, let us start the very first question of the day. Before that, let me present the weightage. In the last 5 years, what was the weightage from this COA subject? If you look at the weightage, in 2022, we have got 6 questions guys, and 2021 7 questions, 2026, 2019 little bit surprised to have only 3 questions, and 2018 6 questions. So this year 2023, definitely I expect 7 questions from this COA. Maybe my personal prediction is you may get around 10 marks from this COA subject this time. This is completely my prediction. Okay, and mostly my prediction works. This time you may get the same number of questions, 6 or 7 for 10 marks from this subject. So guys, definitely please do prepare this subject at the complete level. Okay, let me present the very first question of the day, 2022 GATE question on your screen. A processor X1 operating at 2 GHz has a standard 5-stage RISC pipeline having a base CPI. Base CPI means 1 of 1 without any hazards. Without any hazards, there is a CPI of 1 with clock frequency of 2 GHz. Okay. For a given program P that has 30% branch instructions, control hazards incur 2 cycles stall for every branch. A new version of the processor X2 operating at the same clock frequency, means the same 2 GHz frequency, has an additional branch predictor unit that completely eliminates stalls for correctly predicted branches. So if you could predict, there is no stall. There is neither any savings nor additional stalls for wrong predictions. There is no additional stall, the same 2 stalls if you could not predict properly. And there are no other hazards, it seems. There are no structural and data hazards. If the BPU has the prediction accuracy of 80%, it can predict accurately, then the speed up obtained by X2 over X1 in executing this program is. So guys, tell me what is your answer for this question. Everybody, whoever are watching this session live, please do give your answer. All right. Guys, could you please mark your presence in the chat box? Let me know who are watching this. Sai Gopi says option B 2.43. Okay. What about others? I believe Satya, you are there watching live. Are you? Whoever are live for this session, please mark your presence. Okay, fine. Let's see what is the answer. The answer is 1.43. Gopi, it's not 2.43 dear, it is 1.43. Option A. How, sir? Please observe the given information. Given X1 operating at 2 GHz speed, right? So X1 frequency is 2 GHz, right? And it is having a pipeline with a basic CPI of 1. So cycles per instruction 1. And for a given program P that has 30% branch instructions, control hazards incur 2 cycle stalls for every branch. Okay, 30% of branch instructions give you 2 stalls. What else given? There is another processor X2 with the same frequency but with BPU. If it could predict the branch, then no stalls, otherwise same number of stalls. Otherwise same number of stalls, right? So X2, which is operating at the same frequency, but BPU, if there is a branch prediction unit, if the prediction is a success, no stalls, otherwise same number of stalls, right? And it is also given BPE has the prediction accuracy of 80%, right? So 80% is the prediction accuracy. So now we have to find out the speed up. Yes, everybody, how we find the speed up generally? When you give it as a non-pipelined and pipelined. Non-pipeline speed up, pipeline speed up, generally how we find out? Non-pipelined time divided by pipelined time, isn't it? That is how generally we do. But here we have two processors, X2, X1. So you have to find out the speed up you have achieved through X2 rather than X1. So first of all, how we find out the time? Any time, I mean any processor time. So how do you find the execution time comma T? Number of instructions, generally total time if you want, number of instructions, for every instruction how many cycles, for every cycle what is the time, isn't it? But here number of instructions, yes, we have got number of instructions, no. So we can say it is just a normal unit, normal, I mean you can just take it as 1. Now if there is a stall, I mean if it is a branch instruction, then there are 2 stalls. So for X1 what could be the time? For X1 what could be the time? If there is no branch, then it is 1 plus normal cycles per instruction are 1. If there is a branch, how many branches are there? 30%. For them what is the stalls? 2. So this would be 1 plus 0.6, 1.6, isn't it? Now X2, so what we can take? 1 plus, for branch instructions, if you apply branch predictor unit, if it is successful, what do you mean by successful? 80% prediction successful. So for 0.8 there is no stall, that means 0, plus if it is not successful, then there are no additional stalls it is given, that means the same number of stalls. So this is 1 plus 0.3 into 0.4. This would be 1 plus 0.12, 1.12. Now let us calculate the speed up. ABC Kids Learning Zone hello, I could not answer you now because it's completely irrelevant query you have asked. Please focus on the session. So x1 time divided by x2 time, which is 1.6 divided by 1.12. So what do you get? 1.42. Let us calculate using a CALC calculator. It is 1.16 divided by 1.12. I have done 1.6 divided by 1.12, 4285. Okay, so rounded off to 2 decimal places, we can take it as 1.43. Hence that is the answer. 1.43 is the answer. Got it? Tushar, Gopi, everybody. Next question. Consider a system with a 2 kilobyte direct mapped data cache with a block size 64 bytes. The system has a physical address space of 64 KB and word length 16 bit. During execution of program, 4 data words are accessed in that order 10 times. Hence, there are total 40 accesses. Assume the cache is initially empty. No other data words are accessed by the program. The address of the first bytes of P, Q, R and S are given A248, C280, so on. Right? Now, for the execution of the above program, which of the following statements is or true? What would be your answer? It's a MSQ, dear friends. Please mind it is an MSQ. It's MSQ. Every access to S is a hit. Once P is brought to the cache, it is never evicted. At the end of execution, only R and S reside in the cache. Every access to R evicts Q from the cache. Tushar, Gopi, everyone, may I know what's your answer? Yep. Okay. Let me reveal the answer, guys. The answer is A, B, D. Let's see how. First, let us grab the info from the given question. 2 KB DM cache, block size given, address space given, word length given. So let me first copy this. We are given 2 kilobyte DM cache with block size, with main memory size, physical address space means, and word length. What they are? Block size 64 byte, 64 kilobyte, 16 bit. 64 bytes, 64 kilobyte, 16 bit. And these are the addresses of PQ or RS in the main memory. Now, these are accessed 10 times in the order PQRS, PQRS, so on. Okay, all right. PQRS, 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 so on, accessed 10 times. So total 40 accesses, no problems. Now, it's a direct mapped cache, block size 64 bytes. So first of all, let us find out number of cache blocks. Total number of cache blocks equal to cache size by block size. 2 kilobyte divided by 64 byte. This is 2 raised to 11 divided by 2 raised to 6, 2 raised to 5. So 32 cache blocks are there. Okay. Now, main memory size you know, word length you know. So number of words in main memory, you will get, let's say, 64 kilobyte divided by 2 byte. So we have 2 raised to 15 words. That means you will have 15-bit word address. Because I have converted word into bytes. 16 bits means 2 bytes. So we have actually 15-bit word address. So 15-bit word address is aligned to 16 bits. You can understand from the given. Okay. Now, where we map this? Where we map this? If you observe in the main memory, how many blocks are there? Number of blocks in main memory, 64 kilobyte by 64 byte. You can say there are 1K blocks, 2 raised to 10 blocks. So in the given address, 16-bit, the first 10 bits would be block number, next 6 bits represent word number. Okay. So A248, convert A248 into binary. A248 will have what as the block number? 1010, 10, 0010, 2, 0, 1, 0, 0, 1, 0, 0. This is what the thing. Now, this represents the block number, the other represents the word offset. This is the word offset, this is the block offset in the main memory. Okay. Now, this is main memory thing, guys. This is mapped to what? As it is a DM cache, it interpret it as tag, block offset and word offset. Isn't it? So these 20 bits, sorry, 16 bits, it maps, it interprets as there are 2 bytes, 2 words. So 1 bit for the word offset, and we have 32 blocks. So 5 bit for the block number, and the remaining 10 bits represents the tag. Okay, remaining 10 bits represents the tag. Did we do anything wrong? Everything okay? Yeah. Number of words in main memory. Okay. All right. In this 16 bit, these 5 bits is what represent cache block number. In that way, if I convert this C to 8A also into binary, C means 12, 1100, 2, 0010, 8, 1000, A, 1010, A, 10, and CA 8A, 1100, 1010, 1000, 1010, A262, A 1010, 2, 0010, 6, 0110, 2, 0010. Now please observe, I am bringing from this block. I am bringing from this block. If you observe, this is P, right? P block number of main memory, okay, and this is S block number of main memory are same. Whenever miss occur, what we do? Complete block is copied into main cache memory, right? Not only that word. So it says that P and S are in the same block. P, S are in the same block. P and S are in the same main memory block. So whenever for P miss occur, it bring all the block. That means for S what occur? Hit occur definitely, because that S word is already copied. Okay. Now look at Q and R. This is the Q address and this is R address. Now, in this, please understand these 5 bits 00101, 00101. This is representing cache block number, the underlined 5 bits. That means Q and R map to same cache block. So, when for Q misoccur, you copy. Then when for R misoccur, R replaces Q always. And Q replace R replace Q, Q replace R. In this way, Q gets replaced by R gets replaced by Q, Q gets replaced by R. In this way, every time for Q and R, what occur? Keep occurring miss. And finally, we will definitely have what? This S is as a hit. So observe the options. Every access to S is a hit because it is in the P word. Even the first access is also hit. Once pre is brought, it is never evicted because its cache block number is different. It is block number, let's say 4, and its block number is 5. So it's never evicted. At the end of execution, only R and S reside in the cache. At the end of the execution, only R and S reside in the cache. No, S always reside in the cache. That's why it is false. Every access to R evicts Q from the cache. Yes, that is what we discussed. R always replace Q. Got it? That's why this A, B, D are true. Why option C is false? S always reside in the memory, not from the beginning, not just at the end. Okay? Next question. A cache memory has a hit rate of 0.8 nanoseconds, hit rate 0.8, has an access latency of 10 nanoseconds and miss penalty 100 nanoseconds. Okay. Optimization is done on the cache to reduce the miss rate. Optimization results in the increase of the cache access latency to 15 nanoseconds, whereas the miss penalty is not affected. Okay. The minimum hit rate needed after optimization so that it should not increase the average memory access time. Okay. Average memory access time we can take as hit into cache time, miss into cache time plus main memory access time. This is called hierarchical access. Right? Just if you expand it, it would be h into t1 plus t2 minus h into t1 minus h into t2. So this can be reformulated as t1 plus 1 minus h into t2. That is how this average memory access time got formed. Okay, so let it be equation 1. All right, now we got t1 as 10 nanoseconds and t2 as 100 nanoseconds. Hit ratio before optimization was 0.8. So before optimization, let us calculate average memory access time. Before optimization, T average would be equal to T1 10 nanoseconds plus 0.2 into T2 100. This would be 10 plus 20. 30 nanoseconds was the average memory access time before optimization. After optimization, okay, the answer is 0.85. Let us solve it now. After optimization, the access time should not increase. Let the access time, the average access time be let it be T dash. Okay. So the T dash should not be more than this. So T dash should be less than this 30 nanoseconds, or ideally equal to is also okay, but it should not be more than that. Now, how do you calculate T dash? H into T1 plus 1 minus H into T2. While T1 increased to 15 nanoseconds, T2 there is no change given. If so, T dash, which is H into T1, that is H is what we have to find out. So I am just relating these two, should be less than or equal to 30. H into 15 plus 1 minus H into T2 is what? 100 must be less than 30. So it is 15H plus 100 minus 100H must be less than or equal to 30. I can say minus 85H must be less than or equal to minus 70. Okay, so H must be greater than or equal to 70 divided by 85. Isn't it? What we want? Minimum hit rate. So sorry. I have totally taken the wrong values, wrong formula. T1 only, no? T1 is 15. Right? So now 80 must be less than or equal to 100H. 80 or 85. 115 minus 30, 85. So H must be greater than or equal to 100 by 85. Sorry, 85 by 100. That is how it is 0.85. Right? Hence the answer is 0.85. Any doubts? Please feel free to ask. Shall I proceed to next question? Okay, let us proceed to next question. Let WB and WT be two set associative cache organizations that use LRU algorithm for cache block replacement. Okay, WB is a write back cache and WT is a write through cache. Known thing. Which of the following statements are false? Okay, each cache block in WB and WT has a dirty bit. Okay, every write hit in WB leads to a data transfer from cache to main memory. In write back, okay, every write hit. Eviction of a block from write through will not lead to data transfer from cache to main memory. A read miss in write back will never lead to eviction of a dirty block from write back. Okay, what is your answer for this question? Okay, the answer is ABD. Every cache block in WB and WT has a dirty bit. See, in write through, always both cache and main memory are updated. So, there is no need of dirty bit. But in write back, yes, every block has dirty bit. So, that's why it is false. Every write hit leads to data transfer from cache to main memory in write back? No. Only upon replacement, main memory is updated in write back. So, every write hit will not lead to any data transfer. That's why this is also false. Eviction of a block from write through will not lead to data transfer from cache to main memory. See, you are replacing some block that will not lead to data transfer from cache to main memory. That happens in write back. In write through, always updation happens in both. So, that is, it happens, it is done in write back, not in write through. Means which lead to data transfer. It is given, it will not lead to data transfer from cache to main memory. That's why it is true. This will not happens in write back. A read miss in write back will never lead to eviction of a dirty block from write back. No, it is also false. Okay, so A, B, D are false. Next, which of the following facilitates the transfer of bulk data from hard disk to main memory with the highest throughput? Bulk data in burst transfer, it happens. No need of waiting for this question. Directly we can say it is a direct question, that is a DMA based IO transfer. Yeah. because in burst mode or bulk mode you call it as at high throughput the data can be transferred. Okay, next, assume, okay, we moved on to 2021 year GATE questions. Assume a two-level inclusive cache hierarchy L1 and L2, where L2 is the larger of two. Consider the following statements. Read misses in write through L1 cache do not result in write backs of dirty lines to the L2. True, guys, right? Read miss will not lead to modify or updation of right L2 cache. Write miss will update L2 by L1. Read miss, because the reading doesn't include any modification, there is no need to write back the dirty lines or dirty blocks to L2. That is true. Write allocate policy must be used in conjunction with the write through, and no write allocate policy with write back. What do you mean by write allocate, no write allocate? Write allocate says that if there is a write miss with level 1, it is copied, like you can say there are two levels L1 and L2. If write miss occurs in L1, it is brought from L2. Similarly, if write miss occurs with L2, it is brought from main memory. Means in the hierarchical way, it is written and served to CPU. This is what we say write allocate. Write the memory where miss occurred, then allocate to CPU. No write allocate. If miss occurs with some level 1 cache, directly L2 can supply. If miss occur with L2, directly L1 can supply. So this is like direct access, no write allocate. Hierarchical access for write allocate. In this way you can understand. Now, write allocate policy must be used in conjunction with write through. Not required. Every time we are writing the below levels of memory. So it's not when you use write allocate policy, then only, means if you follow hierarchical access, then only write through will be used. There is no such. Similarly, no write allocate. So it is not mandatory, guys. So we can say false. So which one is false? Which of the following statements is correct? Means S1 true, S2 false. Okay, are you following, everyone? Could you please respond? Are everybody following? Kaushalya. Okay. Great. Next question. Consider a computer system with a DMA support. The DMA module is transferring one 8-bit character in one cycle from device to memory through cycle stealing at regular intervals. Consider a 2 MHz processor. If 0.5% of the cycles are used for DMA, the data transfer rate is. This model we have got earlier also. I mean, in the other years of GATE. In one cycle, 8-bit character can be transferred. That is what given. And it is also given that it's a 2 MHz processor. It says that the clock frequency is 2 MHz. That means what would be the clock cycle time? 1/2 into 10 power 6. I can say 0.5 microseconds. In this time, 0.5% is what used. In this time, 0.5% of the time is what used for DMA. Point 0.5%. Okay, we want per second. So let me keep it in this way. One cycle require 0.5 microseconds. In 1 second, how many cycles? This is 1/2, no? So let me put it in this way. 2 into 10 power 6 cycles in 1 second. Because I want it in bits per second. Now, 0.5% of the time is used for DMA. So 0.5 by 100 into 2 into 10 power 6 cycles means how much? 1 10 power 7 by 100. How much, guys, this is? Ten power 6 by 100. 10 power 4. 10,000. 10,000 cycles in 1 bit, in 1 second. Right? 10,000 cycles. Given in 1 cycle, 8 bits can be transferred in DMA. So when in 1 second, for 1 cycle, 8 bits can be transferred. In 10,000 cycles, how many bits can be transferred? Obviously, 80,000 bits per second. So more or less it's a kind of aptitude question, guys, right? So the answer must be option A. Let's see. Yeah, it is option A. Okay. Kaushalya, Tushar and others. Fine. Let's proceed to next question. Consider a set associative cache of size 2 KB. 2 KB equal to 2 power 10 bytes. It's not 210, 2 power 10 bytes. With cache block size of 64 bytes, assume that cache is byte addressable and a 32-bit address is used for accessing the cache. If the width of the tag field is 22 bits, associativity of the cache. Okay. Okay. We are given 2 kilobyte set associative mapped cache. We don't know the associativity yet. And one block size given 64 bytes, right? And the cache is byte addressable and address length is 32 bits. Okay. As it is a set associative mapped cache, how the address is interpreted as tag set word. The total length is given as 32 bits. Now block size is given as 64 bytes. So 6 bits for the word, because there are 2 power 6 bytes in a block. And tag length is given as 22 bits. That indicates for set 22 plus 6, 28 gone. So 4 bits for the set field. That means there are 2 power 4 sets, 16 sets in the cache. And total blocks per cache, let us calculate. Total blocks in the cache would be cache size by block size. So this is 2 power 11 by 2 power 6, 32. Total blocks are 32. We know generally set associative mapped cache is represented as KWSAM, where K means number of blocks per set. Total blocks are 32 and there are total 16 sets. So number of blocks per set, that is K equal to total blocks divided by number of sets, 2. Hence, what is the associativity? Two-way SAM. It is a two-way SAM. Understood? The associativity must be, yes, 2. Everyone got it? Next, (2021) GATE question again. Consider the following instruction sequence where R1, R2, R3 are general purpose registers. Memory of X denotes the content at the memory location X. So we have got instruction meaning also, instruction size also. Okay. If you want, you may take this instruction sequence photo because there is a continuation to the question. Now, assume that the content of the memory location 5000 is 10, R3 is 3000. Each of the memory locations from 3000 to 3010 is 50. Instruction sequence starts from the memory location 1000. All are in the decimal format. Assume the memory is byte addressable. Okay. After the execution of the program, the content of memory location 3010 is. What's your answer, dear friends? Quickly give your answer in the chat box. Everybody. If you want, I can the content of memory location 3000 is (5000 is 10). Good evening, Mad Mafia. Okay. And the content of R3 is 3000 and content of each of the memory locations from 3000 to 3010 is 50. Yep. What would be your answer? Let's look at the answer. The answer is option A. Why? See, first instruction if you execute, move R1 comma 5000. That means at location 5000 what is there, that comes to R1. So R1 will get 10. Move R2 comma memory location of R3. R3 has what? 3000. That is copied to R2. So R2 is having 50. R2 equal to R1 plus R2. R2 will get 50 plus 10, 60. And move that back to R3. That means in this location 60 gets stored. Okay. Increment R3. R3 becomes 3001. Decrement R1. R1 becomes 9. Branch to 1004. and given the memory location starts from 1000, so branch to 1004 means to this location, branch, if not 0. What not 0? The recently performed operation, what? R1. That is what there in the accumulator. So R1 not 0. Okay, B and Z means branch if accumulator value not 0. Accumulator hold the recently performed instructions result. So what is R1 value? Became 9. That means it branch to here. Move R2 comma R3. So again from 3001 location, what is available? What is there in 3001 location? 50. That is again moved here. Added R1. That means it becomes 59. Stored back. Then R3 becomes initially R3 was 3000, it became 3001, now it becomes 3002, R1 was 10, now it became 9, then it becomes 8. That means how many times it is getting executed? Branch if not 0, 10 times. But how many memory locations we have? These are 10 memory locations. 3010 got not affected. This memory location 3010 not affected. So you will have the same 50. That's why the answer is option A. Got it? Next question. A 5-stage instruction pipeline has stage delays so and so. Okay. Registers that are used between stages have a delay of 5 nanoseconds. The total time to execute 100 independent instructions on this pipeline, assuming there are no stalls, is. Oh, it's a direct question, right? It is n minus 1 plus k whole into small tp. And how do you get small tp? Cycle time, pipeline cycle time. Max of the stage delays plus 1 time of interstage delay, as all are having the same interstage delay. This would be max of 150, 120, 150, 160, 140 plus 5. This is 160 plus 5, 165 nanoseconds. And we have got n as 100 and k as number of stages 5. So just substitute. So TP will be equal to 100 minus 1 plus 5 whole into 165. That would be 99. 104 into 165. One 104 into 165. 17160. Guys, you can use virtual calculator which will be given in the tool. Okay, system will provide virtual calculator, you can use that and prefer to use for such calculations. Don't waste time in the manual calculation. Okay, in the simple, these kind of multiplications, don't waste time by doing manually. I know you people can do it, but you can use calculator to save the time. Okay, so the answer must be option A. Yeah, 17160 nanoseconds. Okay, shall we proceed to next question? Chalo. Here is the next question. Consider a computer system with byte addressable primary memory of size 2 power 32 byte. Assume the computer system has a direct mapped cache of size 32 KB. Each cache block size is of 64 byte. The size of the tag field is dash bits. It's a direct mapped cache. So the CPU generated address is interpreted as tag block offset or line offset, you can say, and word offset, right? Word offset is indicating the number of words in a block, that is block size 6 bits. Why? Because block size is 2 power 6 bytes and total memory has 2 power 32 bytes, so total address length would be 32 bits. Now, when we know total number of blocks, we know the block offset. So total cached blocks would be equal to cache size by block size. That would be 32 kilobyte by 64 bytes. So it is 2 raised to 10 by 2, 2 raised to 9 cache blocks. So 9 bits for the block offset. Now out of 32, 15 gone, 17 bits left for the tag field. So the answer must be 17. Let's see. Yep. Okay. Any doubts? Please feel free to ask. Shall I proceed to next question? Please respond. Okay, Santosh Pant, very good. Thank you. Thanks for the response. Let's proceed to next question. Before that, dear 2023 aspirants, your favorite Rakesh Sir is coming with general aptitude session. In 15 hours, you can gain 15 marks. So just with this session, you can gain 15 marks in just 15 hours, which is coming very soon. And the best combo in the education platform, that is Rakesh Sir and Ankit Sir, is coming up with non-stop mathematics marathon. Means complete mathematics you can cover in just 2 days. In just 2 days, right? So that is also coming soon. So stay tuned. We are coming up with more useful sessions, useful series, and marathons are getting started, right? and complete info we are giving tonight. So stay tuned to BYJU'S Exam Prep for complete info, guys. Now you can download our free ebook and also our scholarship test information, and you will get regular notifications about our workshops if you can subscribe to our BEP channel and register through the link in the description box. Thank you. Let's proceed to 2020 GATE questions. Here is 2020 GATE question. We have, if there are m input lines, n output lines for a decoder that is used to uniquely address a byte addressable 1 kilobyte RAM, then the minimum value of m plus n is. We know decoder configuration is, if you can give n, it makes it 2 power n, right? So n inputs, 2 power n outputs. It's a byte addressable memory. Okay, and of size 1 kilobyte. 1 kilobyte, right? So it's a byte addressable memory and the size is 1 kilobyte. Now, when it is byte addressable 1 kilobyte, that is 2 raised to 10 bytes, means 10 bits required for addressing each byte. So it is given decoder is used to address these 2 power 10 bytes. That means I can say this decoder is getting 10 bit output. I mean, it can produce 2 power 10 output lines with what? 10 inputs. So m would be 10, n would be 2 power 10. So m plus n would be 10 plus 1024, that is 10234. All right. I think the answer should be yes, 1034. Next question. A computer system with a word length of 32-bit has 16 megabyte byte addressable main memory and 64 kilobyte 4-way SAM with block size 256 bytes. Okay. Consider the following 4 physical addresses represented in hexadecimal notation. We got addresses A1, A2, A3, A4. Which one of the following is true? A1 and A4 map to different cache sets, A2, A3 to same cache set, A3, A4 to same cache set, A1, A3 to same cache set. Solve it quickly. I will be waiting for your answer. Yes, everyone. What would be your answer? I am waiting for your answer, dear friends. All right. The answer is option B. A2 and A3 map to the same cache set. Let's see how. These are the given addresses. Before that, we have one word equal to 4 byte, 16 MB byte addressable main memory, byte addressable. So we don't convert into words. We'll keep it in bytes only, as because word length is given as 4 byte. Don't take in terms of words. Okay, it's a byte addressable memory. 64 kilobyte 4-way SAM. Okay, let me write. It's a 16 MB main memory, 64 kilobyte 4-way SAM, and one block 256 bytes. It's a byte addressable. Okay. Now guys, please understand, as it is having 16 megabyte, from here also you can say 1, 2, 3, 4, 5, 6. 6 hexadigits means 6 into 4, 24 bit address it is generating from the given addresses, you can say, or it is having 2 power 4 into 2 power 20 bytes. In that way you can say 2 power 24 bit address. Anyway you can say that this 24 bit address as it is a set associative mapped cache, guys, am I visible and audible? The set associative mapped cache will interpret it as tag set offset and word offset. One block is given as 256 byte, so 8 bits for the word offset, and number of sets if you want, first you need to find number of cache blocks, that is the cache size divided by block size. This is 2 power 10 by 2 square, 2 raised to 8 blocks total. Now when we want number of sets, total blocks by blocks per set, it is given as 4. So this is 2 power 6 sets we have. So remaining 10 bits for the tag. So now the first address 42C8A4, when I take 10 bits 4 2 C 1 1 0 0 1 0 0, this is the 6-bit set number and 8-bit word offset. So A4, right? Then 5 4 6 8 88, 5 4 in binary 8-bit, 6 means 0 1 1 0, 8 means 1 0 0 0 88, and then A3 6A 28 9C. So here 6A will be in the same way, I mean, I don't require that to compare. 2 0 0 1 0 8 1 0 0 9C. And finally, I have 5E4 880. So first 10 bit means 5E 8 bit, and in the 4 0 1 0 0 is what 4, 2 bits gone for the tag, 0 0 8 1 0 0 8 0. So this is a tag, this is a set number, this is word offset. So this is the set number, guys. You can just see for what and what the set number is same. You can see A1 and A4 have same set number. A2 and A3 have same set number, right? A1, A4 same set number, A2, A3 same set number. So A1, A4 map to different sets. No, A1 and A4 same set, A2 and A3 same set. So A1 and A4 map to different set, wrong. A2, A3 map to same set, correct. A3, A4 same set, no. A1, A3 same set, no. So option B is the only right answer we have. Got it? Next. Look at this question. A direct mapped cache of 1 MB has a block size of 256 bytes. The cache has an access time of 3 nanoseconds and a hit rate of 94%. During miss, it takes 20 nanoseconds to bring the first word from the main memory, while each subsequent word takes 5 nanoseconds. The word size is 64 bits. Average memory access time is dash nanoseconds. So average memory access time, if I go with the hierarchical access, it would be h into t1 plus 1 minus h into t1 plus t2. If I go with direct access, average access time would be h into t1 plus 1 minus h into just t2. Okay. This, when we expand, I have shown you it is t1 plus 1 minus h into simply t2. Okay. Okay. Now, t1 is given as 3 nanoseconds plus during miss means 0.06, 0.6, no, 90, 0.6. T2, it takes 20 nanoseconds for the first word, 5 nanoseconds for the remaining words. How many number of words per block? Block size 256 bytes and word size 8 bytes. So 32 words. So remaining would be 31. So this would be 3 plus 0.6 into 175, right? 155 plus 20, 175. So what would be the answer? What would be the value? 0.6 into 175, 105 plus That would be check it out. 10.5. Okay, it is 0.06, sorry. 10.5 plus 3, 13.5 nanoseconds. And if you go with direct access, it would be H is 0.94 into T1, 3 plus 0.06 into 20 plus 31 into 5, because for the remaining words it is taking 5 nanoseconds. So it would be 0.94 into 3, 2.82 plus 0.06 into 175. 2.82 plus 10.5, 13.32. Rounded off, so 13.3. So if you follow hierarchical access, you got 13.5, direct access 13.3. However, in the official answer key also it is given 13.3 to 13.5. So you can give any. Hello Krishna Murari Singh. Good evening. Okay. Shall I proceed to next question? Okay, fine. Next question. Consider the following data path diagram. Consider an instruction R0 is equal to R1 plus R2. The following steps are used to execute it over the given data path. Assuming that the PC is incremented appropriately, the subscripts R and W indicate read and write operations respectively. Okay, so observe for ALU, one input is gone directly, another input is through temp1, and the output is went through temp2 register. Please understand, observe this. Okay, then which one of the following is the correct order of execution of the above steps? Fine. These are given as 1, 2, 3, 4, 5. We know the execution sequence is first instruction fetch, then instruction decode, then operand fetch, then perform operation, then register write, write back or memory. Here operand fetch or register read you can say. Instruction fetch means first address is loaded from program counter to address register. Then program counter incremented appropriately. Then we read, then at this address what is available that comes to MDR, but the fetched one is instruction. So it is supposed to be in the instruction register, hence it would be in the IR. Then control unit decodes it. Then register read or operand fetch. The given instruction, if you observe guys, it is R0 equal to R1 plus R2. So it's a register read. So we will read R1 and R2, then perform operation add, then write back, or memory means it's a write back into the register. So write back into R0. So generally these are what the steps, right? For this, if you see the control signal form, the micro instruction, first PC value should be loaded into MAR. So PC read, MAR write. So PC read, MAR write, and PC incremented appropriately, and then memory read. So these two are given in one, that is 3. So it should happen first. It should happen first. Okay. Then MDR to IR. So I can say MDR read, IR write. So fifth one should happen next, second step. Now control unit decode, read R1 and R2. So if I read R1 and I am sending through temp 1, R1 read, temp 1 write. So this should be the third step. And R2 I am sending directly, because if you observe the data path given circuit, one input I am sending through temp 1, another input directly. So I can say R2 read, temp 1 read, ALU write or add, and that result I can send through temp 2. So these two, perform operation and addition, and write back, these three are given. Okay, not these three, these two, perform operation. These are given together. R2 read, temp 1 read, ALU add, temp 2 write. So it should happen as the third step, fourth step. So, but we want the result in R0. So temp 2 read, R0 write. So this must be the fifth step. So 3, 5, 2, 1, 4. So the correct order should be 3, 5, 2, 1, 4. 3, 5, 2, 1, 4. Option C must be the right answer for this. Let's see. Yeah. Okay. Next, consider the following statements. Which of the above statements are true? Daisy chaining is used to assign priorities in attending interrupts. When a device raises a vectored interrupt, CPU does polling to identify the source of interrupt. In polling, CPU periodically checks the status bits to know if any device needs its attention. During DMA, both CPU and DMA controller can be bus masters at the same time. Which are true? Krishna Kumar Singh, option C, 1 and 3. Exactly. I can say option 1 is definitely false. Both can't be masters. In the interleaved DMA mode, for half clock cycle CPU or half clock cycle DMA controller, right? So CPU DMA controller, again CPU DMA controller, use bus. So both can't be masters at the same time. So definitely option 4 is false. And when a device raises vectored interrupt, CPU does polling to identify the source of interrupt. No. In the non-vectored interrupt, the address is not given, so CPU does polling to identify the source. In the vectored interrupt, from the fixed address, interrupts gets generated. So definitely I can say option 2 is also false. Now, daisy chaining is used to assign priorities in attending interrupts. Yes, it's a hardware form of hardware approach of assigning priorities. So option 1 is true definitely. So yes, there I can find option C is the right answer. In polling, CPU periodically checks the status bits. Software approach. Yep. The right answer is option C, Krishna Murari Singh. Correct. Very good. Okay. Next question. A sudden processor uses fully associative cache of size 16 kilobyte. The cache block size 16 byte. Assume that the main memory is byte addressable, uses 32-bit address. How many bits are required for the tag and index fields respectively in the addresses generated by the processor? Tag is what? Index actually. So after the tag, do we use any other index? No, I think no. Okay, see. Tell me what's the answer for this. Properly the question is not visible. Okay. Now please check. Let me refresh. From my side, actually, it is fine. Could you please refresh once, Krishna Murari Singh? It's a fully associative cache. So actually there is just a tag, guys, and word offset. As block size is 16 byte, 32-bit address, so 4 bits for the word offset, and for the tag 28 bits. So actually index means tag itself. There is no separate index field in the fully associative cache like set index or block index. So I can say it is 28 for the tag, for index 0. Next, the chip select logic for a certain DRAM in memory system design is shown below. Assume that memory system has 16 address lines denoted by A15 to A0. What is the range of address of the memory system that can get enabled by the chip select signal? What would be your answer? Krishna Murari Singh. Option A. Let's see. Yep, it is option A. We have A0 to A15. In this, A12, 13, 14, 15, A11. These are the inputs for this. And we know this chip select will give only one output, and this is the AND gate. We know AND gate will give 1 when all inputs are 1s. If all inputs must be 1s, if you see A13 and A12 are complementary inputs, that means these should be 1, 1, 0, 0, 1. So, A15, A14, A13, A12, A11 must be 1, 1, 0, 0, 1, and from A10 to A0 they can be any. So, the start would be all zeros and the end must be all ones. So, this would be in hexa, if I take, this would be C8 002 CF. This is all 4 ones, right? So, CF FF. So, this must be the range. Yeah. Good. Next question. The instruction pipeline of a RISC processor has the following stages: fetch, decode, operand fetch, perform operation, write back. W, IF, ID, OF and W takes 1 clock cycle each for every instruction. Consider a sequence of 100 instructions. In the PO stage, 40 take 3 cycles, 35 take 2 cycles, remaining 25 takes 1 cycle each. Assume that there are no data hazards and no control hazards. Okay. The number of clock cycles required for completion of execution of the sequence of instructions is. Yes, what will be your answer for this question? Two nineteen. See, we have total 100. In that, other stages take 1 clock cycle. For 25 instructions, the PO stage takes 1 clock cycle. So, total time, if I want, number of stages are actually 5. So, K so I can say it is for 25 instructions. Wait, for all the instructions, let me take for 100 instructions, 1 clock cycle is common, minus 1 plus K, 5 into 1 plus, for 35 instructions there is 1 stall, 1 extra cycle for PO. For 40 instructions there is 2 extra cycles. So, this would be 104 plus 35 plus 80, 184 plus 35, 219. Okay. Next, the size of the physical address space is 2 raised to p bytes, word length 2 raised to w bytes, capacity of cache 2 power n bytes, size of each cache block 2 power m words. For a k-way set associative cache memory, the length of the tag field is. Physical address space is 2 power p bytes. So p bit, okay, word length given, no? Fine. So number of words in main memory. Two power p bytes is what main memory length. 2 power w bytes is what word length. So 2 raised to p minus w bytes, p minus w words we have. That indicates p minus w bits for each word. Now it's a k-way SAM. It's a k-way SAM. So number of cache blocks equal to cache size by block size. Cache size 2 power n bytes. This is 2 power m words. I can say it is 2 power n bytes divided by 2 power m words. One word is 2 power w bytes. So this is 2 power n minus m minus w. So we have total 2 power n minus m minus w blocks. Now number of sets would be equal to total blocks by blocks per set k. Now this p minus w bit is given for tag. Set of set would be log 2 power n minus m minus w divided by k base 2 for set of set. Word offset, every block is having how many words? 2 power m words, so m bits. Now if you expand this, p minus w equal to tag bits plus, it is log a by b, log a minus log b, and again log 2 power x base 2 x. So I am directly writing it as n minus m minus w minus log k base 2 plus m. So plus m minus w. So tag is equal to p minus n plus log k base 2. Option B will be the answer. Okay. All right. Next question. The following are some events that occur after a device controller issues an interrupt while process L is under execution. Which of the following is the correct order in which the events above occur? Krishna Murari Singh. What would be your answer? Let's see the answer. It's option A. Definitely, first the current instruction execution is completed whenever an interrupt occurs, because it is generally treated as maskable interrupt and external interrupt, no? And then the processor pushes the process status of L. What is L? The current process onto the control stack. Then the new PC value based on the interrupt is loaded, and then execute that interrupt service routine and pop the L from the stack. So definitely it's the correct order, QPTRS. Fine. Next, consider the following processor design characteristics: register to register arithmetic operations, fixed length format, hardwired control unit. Which of the characteristics above are used in the design of RISC processor? Direct question. These are all RISC processor design characteristics, right? RISC use only register operands for arithmetic operations, load store architecture, fixed length instruction format, and hardwired control unit uses RISC. RISC processor means you can say hardwired control unit design use RISC. Got it? Okay, that's all. The last 5 years PYQs of COA. Of course, we have a few more, but let us conclude the session with this. This is my Telegram group link. If you have not joined yet, please do join to connect with me for doubts, any guidance, PDFs, and also you can connect with your friends who are appearing for the same GATE exam. Okay. Thank you for joining this session. Please do like the session, share, and subscribe to our BYJU'S Exam Prep channel. And guys, we are starting marathons. Regularly, please attend these marathons. They will be very, very helpful to you. So when, what subject, how many questions, everything, all the details will be disclosed to you tonight at 10 PM session. So without fail, attend that session. Okay. Thank you so much for joining. Keep attending the sessions regularly. Keep learning, keep growing. See you in the next session. Till then, have a great time. Take care. Good night, everyone. Bye-bye.